Hey everyone, and welcome. I want to give a huge shout out to Professor Payne and her amazing calculus students over at Los Angeles City College. Professor, your dedication is awesome. And students, get ready, because today we're about to add some seriously powerful tools to your calculus toolkit. Let's get right into it. So, you've gotten pretty good with the power rule, right? I mean, finding the derivative of x squared, x cubed, no problem. But then, bam, you run into a function like this one, x to the power of x. And suddenly, everything you know kind of grinds to a halt. Your trusty power rule just doesn't work here. Why? Because the base is a variable, but so is the exponent. This is a whole different ballgame, and we're going to need a completely new playbook to solve it.
And this right here is the key difference we've got to wrap our heads around. On the left, that's the power rule you know and love. Variable on the bottom, constant up top. But on the right, that's what we're tackling today, an exponential function. The base is a constant, and the variable is up in the exponent. They might look kind of similar, but in the world of derivatives, they are completely different animals. And trying to use the power rule on an exponential function, that's probably the #1 mistake people make. So we need a new set of rules.
So here's our game plan for today. We're going to kick things off by introducing the 2 essential rules for these new functions. Then we'll see how to power them up with the chain rule. After that, we'll learn a pro-level move to solve that tricky problem from the beginning. And finally, we'll connect all of this to what's happening right here in Los Angeles.
All right, let's dive into our first topic, what I'm calling the core duo. We are about to add 2 foundational must-know rules to our arsenal. They're all about the natural exponential and natural logarithm functions. And trust me, these 2 are the key to everything else we're going to do today.
And this first rule is, well, it's kind of magical, honestly. The number e is just special. It's the one and only base where the function's derivative is just itself. Think about what that means. For the function e to the x, its height on the graph at any point is exactly the same as its slope at that very same point. It's the purest definition of exponential growth you can get. It's incredible.
So if that's one side of the coin, what's on the other? The natural logarithm. The derivative of the natural log of x is simply 1 over x. And this isn't just some random rule you have to memorize. No way. It's deeply and beautifully connected to the e to the x rule, all because they are inverse functions. Let me show you what I mean.
This graph just shows that connection so perfectly. You can see how e to the x and the natural log of x are perfect mirror images of each other across that y equals x line. And that reflection has this amazing effect on their derivatives. So if you find the slope on the e to the x curve at the point 1, e, you'll find that the slope is exactly e. Now hop over to the mirror image point on the natural log curve, which is e, 1. And guess what the slope is there? It's 1 over e. The slopes are perfect reciprocals at their corresponding mirror points. So cool.
Okay, so we've got our 2 main rules down. Awesome. But what happens when things get a little more complicated? You know, when it's not just e to the x, but maybe e to the power of 2x. Well, for that, we need to call in a trusty old friend, the chain rule.
This table shows us how to handle pretty much any situation. For any other base a, it's basically the same rule with a little correction factor of ln of a. But here's where it gets really important. Focus on those bottom 2 rows. When the thing up in the exponent or inside the log is a whole other function, which we call g of x, the chain rule has to come out and play. You see that extra g primed of x multiplied at the end? That's the chain rule in action. You absolutely cannot forget it.
Look, the chain rule is your best friend here. It's what unlocks the real power of these functions. But let's be real, it's also where almost everyone messes up at first. Forgetting to multiply by the derivative of that inside function is such a classic mistake, so don't feel bad if it takes a second to click. Once you get in the habit, it becomes second nature. And here we have a perfect example of that trap. This is from actual student work. The student is trying to find the derivative of e to the 2x. They did the first part right. The derivative of e to the something is e to the something. But then, they just stopped. They forgot the most important part of the chain rule.
So let's break down how to do this the right way. On the left, that's the common error. On the right, that's the correct approach. You start with e to the 2x, sure. But then, and this is the key, you must multiply by the derivative of the exponent, of the 2x. The derivative of 2x is just 2. So the final correct answer is 2e to the 2x. It's that simple, but also that easy to forget. Just always ask yourself, what's the inside function and what's its derivative?
Okay, you ready for the main event? It's time to go back and face that impossible problem from the very beginning. For this, we're going to need a special technique, what I like to call the pro move. logarithmic differentiation.
So here we are again, staring down y equals x to the x. It's not a power rule problem. It's not an exponential rule problem. It's this weird hybrid that seems to break all the rules we have. So what do we do when the rules don't apply? We change the game.
And here's how we do it. It's a simple three-step process. First, and this is the magic key, you take the natural log of both sides of the equation. Why? Because of our log laws. That lets you take that variable exponent and bring it down in front. Step 2, you differentiate both sides. And finally, step 3, you just do a little algebra to clean it up and solve for y prime, which is the derivative you wanted all along.
And when you run our mystery function x to the x through that three-step process, voila! This is what pops out. The derivative of x to the x is x to the x times the quantity 1 plus the natural log of x. That impossible problem, solved. This technique is your secret weapon for any function that has variables in both the base and the exponent.
Okay, so that's some really cool math, right? But what's the point? Why does any of this actually matter? For this last part, let's bring it all home. Let's talk about why this stuff is so important for your future STEM career right here in Los Angeles.
These functions, exponential and logarithmic, they are the language of dynamic change. Here in LA, that means modeling how fast our communities are growing. It's calculating decay rates for medical imaging over in the biotech hubs. For the aerospace engineers, it's analyzing how quickly heat transfers. And for all those tech startups over in Silicon Beach, it's all about modeling user growth and compound interest. This math is literally everywhere in this city.
Let's make it super concrete. Say this function models a community's population. It starts at 500,000 and grows at 5% a year. Now, before today, you could plug in a time like 10 years and find the population at that time. But now, with the tools you just learned, you can find the derivative. You can find the instantaneous rate of change. You can calculate exactly how fast the population is growing at any single moment. That is a whole new level of insight.
And really, that's the whole point. This is what a derivative truly is. It's a sensitivity meter. It answers one simple question. If I nudge this input just a tiny little bit, how much does the output respond right now? Whether the input is time and the output is population, or the input is an investment and the output is your profit, the derivative tells you how sensitive that relationship is at that very instant. So think about it. You started this explainer looking at a problem like x to the x and thinking, how on earth do I solve that? You're leaving with a powerful new set of tools in your toolkit. Tools that describe and predict the kind of exponential change that shapes our entire world, from biotech to finance, right here in our city. You now have the language to model incredibly complex dynamic systems. So the only question left is, what are you going to build with it first? Thanks for watching.